You mentioned core dump, like in the first few slides, the open core dump. Yeah. So I'm just curious how this is practically used.
Well, the way that is practically used is if you have a code that has been compiled with debugging information, in other words, with -G, and that code crashes, it will generally produce a core dump. Now, in some systems, you might not see it because core dumps are usually very large, and some system administrators disable the ability of codes to produce core dumps. But if you get one, there will be a lot of debugging information inside. What you can do is you can open this core dump with DDT, indicating DDT also what the executable was, and then you will be able to go through that information and try to find out exactly where the code crashed and what the reason was. I can actually not tell you a lot of detail about once you open the core dump what options you have to analyze it inside DDT, because this is not something I do on a regular basis. But the idea is that even though you didn't run a debugging session, if you had a code that was executed with debug information in the binary, you will get some debug information in this core dump, and you should be able to access it with DDT afterwards. Does that answer your question?
Yeah, it's very helpful. Because what I'm trying to think about is for those transient problem which can take months to run. I mean, normally we write log files. I mean, the debugging is essential, but we need to keep track of a lot of things and see if they're working for each procedures. So the log files normally help us to locate the long-term bug. I mean, I'm not talking about those small bugs. I'm talking about based on our logic, maybe the logic fails at a certain point. That's why we keep track by ourselves. So do you have any comments on how we supposed to do these things?
Well, I mean, the main problem there is that if you want to run with debugging information in the binary, you're probably running with a non-optimized binary, which will reduce your performance tremendously. That's the main problem I could see there. If you're willing to compile with both debugging information and a high level of optimization, which you can do, then you could probably get some information out of the core dumps. But it depends very much on the application, because these core dumps are pretty large, and if you're only getting failures at a very rare rate, I'm not sure how helpful this could be. And definitely, if you already have core dumps, you should use them. But it might be the only way to actually debug something that you know only presents a problem every 2 months or something like this.
Yeah, so what if I compile with the release mode, not the debugging mode, and log the system by ourselves, like kind of a maybe sophisticated ones? So is there any practical ways which can help us debug in the middle, you know, without actually recording the debugging information? I'm just curious if there are anything like that.
Well, again, depending on the code, if you know that there are some parameters that you can track consistently, and that if they get out of a certain range, or if they start showing a particular trend, what you could always do is you could regularly calculate those and save them to a small log file, and that will help you track the evolution of different sections of the code. But that is so code specific that it's a little bit difficult to give you any more specific advice, really. What you're doing is probably what makes sense, to create small logs that you save regularly with a few variables that you track, not with the whole fields, but just with a few variables that you know you can calculate and track, and give you information about different sections of your code and how they're behaving. For me, that would be the only thing that would help if you don't want to run with debug information inside the binary.
Okay, thank you.
You're welcome. Okay, so if we don't have any more questions, what I'm going to do is I'm going to start a debugging session with DDT on Ranger. So one of the first things that you have to do when you log into one of these systems and you want to use DDT is make sure that your X Windows is working properly. So a very silly test is just to run xclock. Make sure you can see it on your screen, because if you don't, then like me right now, you probably have a problem. Might have booted me out. Let me just connect again. Just give me a second to connect again. I think Ranger booted me out because I was too long without touching it. Okay. Okay, so I'm ready to go. What I'm going to do is I'm going to load the DDT module. Let's make sure it's there. And I'm going to get the example codes that I gave you before. Can you actually see anything on that screen? The font is probably too small. So I'm only going to do a tar xvf of that train 00/DDT underscore petascale.tar. So that has created a new directory called DDT underscore petascale.
Can you unalias your ls?
Sorry, say that again?
If you could unalias your ls, we could get rid of that color.
If I could what? I didn't get it.
Okay, now it's fine. Now it's not showing any colors. Okay.
Ah, okay. So I'm just going to, the first thing I'm going to do is I'm going to compile the sequential code and I'm going to run it. I know one shouldn't run on head nodes, but this takes about half a second, so I'm going to do it. And you can do it too. I mean, that's not a breach of anything. In my case, I like the Intel compiler, so just ICC -G -00 cell underscore sequential dot C.
So that's asking if you can response those.
Not in PuTTY. Okay, I know the font size is very small, but I'm only going to run two commands here, which are the compilation, and then I'm going to invoke DDT. So I hope you can keep up with me for those 2 seconds. What I was saying is that I'm just going to compile with the debugger flags cell sequential.c. I'm just going to call it sequential. So I'm going to run it with an array of size 64, and actually, well, I'm hoping that most of you are familiar with the example that Leigh ran yesterday for TotalView. But perhaps I should show you what I'm going to do first. So let me show you. This is the problem that I'm actually going to deal with. I have an array that is filled with integers. I'm just initializing those values in a particular way using a modulus operation. And this array is essentially periodic, 1D. And I'm going to do that operation that you see there, essentially grabbing both of my neighbors at every step. I'm going to do this with a serial code, which is a pretty simple thing to do. And I'm also going to do with MPI, which means that I have to break that array into different subarrays for different processes. And I have to allocate a certain level of ghost cells at the edges for the communication between those processes, because when I use values that are right at the end, I will need to grab some data that used to be my neighbor process. For example, to calculate these 5, I will have to grab that 6 from my neighbor process from the previous step. So that means that I would have to allocate some extra space on both ends of the array. There's also an OpenMP version where each thread deals with a section of the array, and there are therefore you have 3 different codes in the hands-on session. One is for the MPI version, one is for the OpenMP version, and both of those are wrong. So both of those have at least 3 or 4 errors in the code that you need to fix. What I'm going to do is I'm going to run the sequential code first, because that code is clean. I'm going to get an output from it, and while I debug, I'm going to watch for my output, because not all my problems in the code are going to lead to crashes. Some of them are just going to lead to a wrong output. So what I want to do is I'm going to run the sequential code first, just with 64 elements in the array and 10 iterations. And this is irrelevant. You can use any number, but if you're running on the head node, don't put 20 million iterations, because somebody is going to get upset with me. So just try to keep it to a small number, because for debugging purposes it's plenty. And what you will see is that the output of the code will give me a maximum and an average value. And I know you cannot see them right now, but the maximum in this case is 8, and the average is 3.968, whatever. It is irrelevant. The only thing you need to remember is that you want to write this down so that when you run the other codes, you can compare your outputs with these values. So now that I have written somewhere the values that I get from the sequential code, I'm going to compile my parallel code full of bugs, which is cell_mpi bug.c, and I'm going to compile it with debugging information and without any optimization, and I'm going to call it mpi_bug. So that's it. I have my new executable, and now I'm going to run DDT. Then the name of the executable, which is mpi_bug, and then the command line arguments for the code, which are 64 for the array length and 10 for the number of iterations that we do over the array. Okay, and we get the familiar DDT welcome screen. I'm going to just run and debug a program. So if I minimize this, you can probably still see the background. Okay, so this is the configuration screen that I was talking about before. Well, the font is pretty small, but if you trust me, this thing I'm highlighting here is the full path to my executable mpi_bug. In the argument section, you will see that DDT has already captured the 2 arguments I used, 64 and 10. Now there's a box here that says run without MPI support. This is obviously not what I want to do, so I just leave that as it is. And I'm going to go through the options one by one.